Okay, evening everyone. Evening. I hope you are all well. Uh, Welcome to our today's lesson regarding chapter 4 and chapter 5. I will try to do as much revision as I can in terms of explaining to you how you must answer questions regarding your BJT. Now, I've already released the scope so that you can go through the scope, of which I think I did it on Saturday. And I hope you all got time to sit down and go through everything that I have mentioned that you must go and have a look at according to the information that you need for your test 3. Okay. Now, I will take this initiative of doing the circuit analysis in terms of the transistor biasing. So, which means it can be transistor circuit analysis in terms of looking at one type of a bias. Now, remember, on our discussion in class, we did 2 biases. We did the first, which was your base bias. And when we did the base bias, on our circuit analysis on that bias, we were trying to see how the transistor will start to operate in terms of the collector characteristic curve. Now, with the collector characteristic curve, you will see that we looked at 3 regions, which is your saturation region, which is your cutoff region, and also which is your active region. Now, each and every analysis of the transistor will have to work or must work according to the collector characteristic curve. And there was a question which was brought to me regarding that some of you couldn't figure out how do I work with a transistor collector characteristic curve. Where do I find this? Where do I find that? How do I do this? And how do I do that? Now, I will try by all means to explain all of those concepts so that you can see how you can relate all these transistor circuit into your collector characteristic curve. Now, I will take an example of a collector, sort of a voltage divider circuit, whereby with this voltage divider circuit, we'll do the analysis, of which when we do this analysis, then at the end, then we will summarize it to a point whereby now we will take or we will define the characteristic of how the transistor is working into a collector characteristic curve. Now, if you are given a bias transistor, now with your bias transistor, then I will go and say, on this transistor of mine, I have the following as a circuit. Whereby this is your R1, this is your R2, This is your RC, and that is your RE. Then you have got your Q1, which is your transistor. And then with this, then we're going to say, let's assume that beta DC of this transistor is given as 120. Then we're going to say our RE, for example, is given as 1,2 kilo ohms. I hope this circuit of ours will work. And then our RC, let's say it's given as 2,2, or let's say 2,7 kilo ohms. And then here we say here, let's for example, is given as 333 kilo ohms. I hope you're following this. And then let's say here is given as let's see what we can name this. Okay, let's just say 20 kilo ohms. Yeah, somewhere like this. Okay, now then we say here our VCC is given as 15 volts. Our VCC is given as 15 volts. Now, when we do our circuit analysis, you will see that there are key points elements that we need to determine, of which our key elements that we need to determine, we will have to go and find how the current it is flowing within your transistor, of which this current that they are talking about, you will see that it will be your base current, it will be your emitter current, and also your collector current. Now, with the emitter current, sorry, with the base current, which is flowing. Now, base to emitter connection, it must be forward bias. At the same time, your base to, your collector to base must be reverse bias. Now, this simply means that if you look at the following structure, which is your DC analysis, if you look at the following structure, which is your DC analysis, this simply means that your ideal DC of a transistor, I've already discussed this issue with you, whereby your ideal DC analysis that is your ideal DC analysis. Now, with this ideal DC analysis, it simply means that your collector is there, your emitter is there, and then your base is there. Now, with this configuration, remember, this is where you find your gain. This is where you find your gain. Now, your current, it must be the collector current, it must be the base current, then it must be the emitter current. Now, with this, it simply means that your base current, which is this current here, must force your base to emitter configuration to go into forward bias, which means from here to here, that is where you will find your your BE connection. Now, your BE connection, which means the point between the base and the emitter, that is when this diode, it is being switched on. When this diode is switched on, which means it will be forced to go into forward bias mode. Now, when it is at forward bias mode, it will generate a barrier potential of 0.7 volts. Now, when this generates a barrier potential of 0.7 volts, then your base to collector configuration, that is your CB, your base to collector configuration, it must be reverse bias, which means there must not be any connection which is existing here. Your base to collector must be at reverse bias. Now, with your base to emitter, with your base to collector at reverse bias, then you will see that now you force your collector to emitter. You force your collector to emitter, whereby now you will see that you have your VCE. Now, once you have the VCE, this is where now you go and determine what will be your output. Now, at these 2 points, that is where you determine what will be your output. And remember, your collector current, it is base current dependent. When your collector current, it is base current dependent with this gain, then you will see that if that it is possible, when your IC starts to flow, your IC will be your beta DC multiplied by your IB. Your beta DC multiplied by your IB. Remember, your collector current, it is base current dependent. Your collector current, it is base current dependent. Now, coming back to this circuit of yours. Now, this just gives you an idea of what is happening within your Q1, which is your transistor. If you get to understand this transistor, then it becomes the replica of what is happening here in terms of the functioning of your transistor. Now, when we work with this type of a circuit, when now we want to see how the transistor or the characteristics of the transistor it is occurring. Now, I hope you have got your calculators, and please give me the correct values, not like last time whereby you were giving me wrong values. I don't know how you punch it into your calculators. Now, then we're going to say, when we work with this type of a circuit, we will want to find these elements, which means with these elements flowing, then it makes it easier for us to define exactly what is happening. Now, with the definition of what is happening, which means now we're going to say, if I have got IB flowing, which means VB is generated at that point there. When IE is flowing, which means VE is generated at that point there. When IC is flowing, which means VC is generated at that point there. Now, once these elements have been identified, then we can define the characteristics of our working transistor. Now, for us to do that, especially when we work with a voltage divider bias, then we're going to say there are steps that one needs to follow in order to do this analysis. Now, then we're going to say step one, that one needs to follow. We need to test the stiffness of our transistor. When we test the stiffness of the transistor, now we need to check if our transistor, it is stiff or it is not stiff. We need to check our transistor if it is stiff or not stiff. And for us to do that, then we're going to say, because the connection of the base, it is a wire which is connected in between your R1 and your R2, which means there is no specific resistor which is connected into that base there. Now, then we're going to say, let's go and determine this magnitude. The determination of the magnitude, that is your R in base, which is your imaginary base resistor. Now, with this imaginary base resistor, it will be R in base. It's given by beta DC multiplied by your RE. Beta DC multiplied by your RE. Always remember these steps, because these are the steps that one needs to follow in order for one to determine exactly how he or she must do this analysis. Now, with this R in base, we know what is beta DC. Beta DC is given as 120 multiplied by your RE, which is given as 1,2 kilo ohms. Your beta DC, which is given as 1,2 kilo ohms. Now, those that keeps on doing the mathematical calculation and you skip the units in full, please stop doing that, because you lose marks based on the fact that I don't know what you are in a hurry for. Then you keep on removing your units. Now, stop removing your units, and also not your units, your notations. Stop removing notations. You will see that I'm using engineering notation, which is kilo. So which means I must include this kilo, so that I don't just go and write 120 multiplied by 1,2. Then you stop there. Then you forgot that this is 1,2 kilo ohms. Now, if I go and say 120 multiplied by 1,2, what will it give me? Can I have one person who can tell me the values? Anyone? Just unmute your mic and then you tell me.
144 kilo ohms. 144 kilo ohms.
144?
Yeah.
You must make sure that that is a correct value. 144 kilo ohms, which is your R in base. That is the first step. Now, I want somebody to second that. Someone please second that.
Correct, sir.
It's correct.
Good. Okay, good. Now, once you get this R in base, then the next step, you need to go and say, now, if I want to test the stiffness, for the transistor to fall under stiff, which means R in base must be greater or equals to 10 times R2. If the transistor is not stiff, then your R in base must be less than 10 times R2, which means in this case, are you saying something? Okay. In this case, then we're going to say, so let's go. Your mic? Okay. Can you, yeah. Okay. Then in this case, now I'm going to say, what is 10 times R2? 2. This 10 times R2, it will be 10 times your R2, which is 20 kilo ohms. What is 10 times 20 kilo ohms?
200 kilo ohm.
200 kilo
ohm.
ohms. Can I have someone to second that?
Correct.
It's
Good.
correct.
Good. Now, once you get this 10 times R2, now we need to go and do the comparison. When we do the comparison, now with this comparison, which means now it is your R in base compared to 10 times R2. Now, with this comparison, we are checking if the transistor it is stiff or not stiff. Now, if we go to this one, R in base it's 144 kilo ohms. 10 times R2 is 200 kilo ohms. Is it R in base greater than 200? Is it 144 kilo ohm greater than 200 kilo ohm? It's a question.
No. No.
Eh?
No. No.
It's 144 kilo ohm greater than 200 kilo ohm. It's a
No,
question
sir.
that
No, sir.
it is no. Which means this transistor, in the case of this stiffness, if we look at 10 times R2, you will see that R in base, it is less than 200 kilo ohm, but it is not greater than, which means this stiffness, it is out. Then on the other side, which means it is not stiff, because 200 kilo ohm, it is greater than what? 144, which means your R in base, it is less than 200 kilo ohm, which means your transistor, it is not stiff. Now, once we generate that the transistor it is not stiff, then we'll go and define that our transistor it is not stiff, which means we have tested the stiffness of our transistor. Up to so far, are we together?
Yes, sir.
Good. Now, once we generate these, then we come to the next step, which is step 2. Now, in step 2, based on the stiffness, based on the stiffness. Now, based on the stiffness, if your transistor it is stiff, then our VB, which is the base voltage, will be given by our VB, which is the base voltage, will be given by, now, when you determine the base voltage always, you will find it from your resistor R2, which means resistor R2 will generate enough voltage so that you will have the current which is flowing into the base of your transistor. Now, VB in this case will be your R2 divided by your R2 plus your R1. All of these, it is supplied from what? It is supplied from your VCC. That is when your transistor, it is stiff. Now, if your transistor, it is not stiff, which means your VB will be given by, now you will go and say, this inside base resistance that we have determined, this inside base resistance that we have determined, which means it needs to be parallel to this R2, which is into our circuit. Then I will go and say your R2 is parallel to your R in base, divide by your R2 parallel to your R in base plus your R1. All of these multiplied by your VCC. Now, these are the two equations that you need to work with. But now, you don't just pick and choose. It doesn't work in that way. It needs to satisfy step one. Once step one it is satisfied, when you move to step two, then it gives you a lead direction to how are you doing your base voltage. Are you doing your base voltage on a stiffness or on a not stiffness transistor? On when the transistor is stiff or when the transistor it is not stiff? Because we have generated that, or our R in base compared to our 10 times R2 indicated that our transistor is not stiff. If it is not stiff, which means now I will go and say, now my R in base, sorry, my VB will be given by an equation when the transistor it is not stiff, which means I need to follow this equation here. Do we understand each other? Okay, now once I go and do that, then I'm going to say for me to move forward, let me just write a line there. Now for me to move forward, now on step two I will say I'm finding VB, but I am finding VB when the transistor it is not stiff. Now with this VB, now I need to go and say, let me find what is R parallel to R2 parallel to R in base. Our R2 parallel to R in base, then I will go and say my R parallel, the one that I'm talking about, will be given by R parallel, the one that they're talking about will be given by your R in base, which is 144 kilo ohms multiplied by your R2, which is 20 kilo ohms, divide by your 144 kilo ohms plus 20 kilo ohms, which gives me what?
$17.56 kilo ohm.
17.56. 3 decimal places after the comma.
561.
561. Huh? 561. Any seconder?
It's correct.
Okay, good. Now, that is our parallel resistor, which means now we have determined this parallel configuration here. Then I will go and say, once I determine this, now my VB, it will be your R parallel. Remember, this is your R parallel, the one that you have determined. Divide by your R parallel plus your R1. Now, multiply by VCC. This R parallel is replaced by this one here. Don't forget that. Which means in this case, I will go and say R parallel, which is my 17,561 kilo ohms, divide by 17,561 kilo ohms plus, what is your R1? Your R1, it is 33 kilo ohms. All of these multiplied by VCC. My VCC, it is this VCC here, which is 15 volts, which gives me what?
5,209 volts.
5,209 volts. Did you get that one? Second,
5,21, sir.
3 decimal places after the comma.
Yes, after the comma,
5,291.
it's 2098. It's 5,21 volts.
It says 5,2098,
Yes, sir.
which means it's going to be 5,210
1
1.
volts. Yes, sir.
Please learn how to do the rounding off. Please learn how to do the rounding off. Now, that is your base. Are you saying something? That is your base voltage. Now, once you get this base voltage, then you go and say, now I need to go and determine what is my emitter voltage. What is my emitter voltage? For me to determine the emitter voltage, then I will go and say my VE will be given by your VB minus VBE, which is this emitter voltage. Remember, this is the emitter voltage. You have got the base voltage, which means now your current is flowing in this direction. I need to know what is the emitter voltage. With the emitter voltage, which means it is going to be the supply voltage, which is the base voltage minus the diode voltage, then it will give you the emitter voltage, which is at that point there. Now, in this case, it's going to be 5,210 minus the voltage across the base. It is 0,7 volts, which gives you what?
4,51 volts.
4,51 volts. That is what you determine. Ma'am?
Yes, sir.
Second,
Yeah, sure.
It's
okay.
10. 4,510.
4,510 volts. Now, once I've determined this VE, then I will go and say, now, if this is the VE is from the emitter to the ground. VE is the emitter to the ground. Then, now I will go and say, now I can find what is my IE. When I want to find what is my IE, I will go and say this IE will be given by VE divided by my RE, where my VE, it is 4,510 divided by my RE, which is 1,2 kilo ohms, which gives me what?
3,758 milliamps.
3,758
milliamps.
3,578.
3,758.
Oh, 3,758 milliamps. Second,
She's correct, sir.
okay. Now, that is my IE. Now, once I get to this stage, then I will go and check. Remember, it needs to have a leading direction. Now, Now I need to go and check what we call my step 3. My step 3, I need to go and check, must I assume that IE is equivalent to IC? Or must I not assume that IE it is not equivalent to IC? Now, these are the two conditions. Condition 1, must I assume that IE is equivalent to IC? Or must I not assume that IE is equivalent to IC? Now, it's either it is given in this manner that you must assume that IE is equivalent to IE, or you must not assume that IE is equivalent to IC. Now, if, for an example, now I say, I am not assuming that IE it is equivalent to IC. I am not assuming that IE is equivalent to IC. If I am not assuming this condition, let me just write it here, which means now in step 3, I am not assuming that IE is equivalent to IC. If I am not assuming this, let me just say continue step 3. I am not assuming that IE is equivalent to IC. Now, then I will go and say, I need to find this IC. But for me to find IC, I know that IC, it is gain DC multiplied by IB, which means it is beta, so it is IB dependent. Now, IB, I must go and determine what is IB. Now, for me to go and determine this IB, then I will go and say, now I have to go and find, this is your IB. And for you to find IB will be given by I of R1 minus I of R2. Now, the current which is flowing through R1 to a junction and the current which is flowing through R2 a junction, now it will create the current which is going into your base. The total current is generated by the supply, which means the current in this direction, that is your IR1. Now, when you look at this current, the current entering the junction is equal to the sum of the current leaving the junction. The sum, it is the current which is going into IR2 and the current which is going there. Now, for me to do IB, then I must go and do the manipulation of this configuration, and that manipulation now it leads me to IR1 minus IR2. Then I've determined IB. Now, that it is only existing when I didn't assume that IE is equivalent to IC. Because I didn't bring that assumption, then I will go and say, now I need to find what is IR1. And for me to find what is IR1, then I will go and say, oh, IR1 will be your VCC minus which is the supply voltage. Remember, I'm talking about the current here. VCC minus VB divided by your R1. Your VB, it is the voltage across that one here, which means this voltage plus that voltage must give you that voltage there. I hope we understand each other at this point of time. Now, then I will go and say, in this case, what is my VCC? My VCC, it is 15 minus, what is my VB, which is 5,210, which gives me what? Sorry, divide by R1, in this case, which is 33 kilo ohms. Come.
296,667 microamperes.
296,
667
667 microamps. That is my IR1. Now, once I determine my IR1, then I'll go and say, now I need to go and check what is my IR2. Whereby my IR2, it is the current flowing here. Remember, already I find what is VB, because my VB came from here. Remember, your VB came from here. Then I will go and say, now I need to see, what is my VB? My VB divided by my R2. What is my VB? In this case, my VB was given by 5,210 divided by 20 kilo ohms, which gives me what?
260,5 micro.
is 260,5.
260,5 micro amps. Now, that is my IR. Which one is that one? Sorry. Yeah, that is my IR2. Now, once I determined these, then I will go and say, on the equation, I have got IR1, I have got IR2, which means I can go and find what? I can go and find my IB. For me to find the IB, it is going to be 296,667 microamps minus 260,5 microamps, which will give me what?
And 36,167
36,167 what? Micro amps. That is my IB. Now, once I find this IB, we know that from the beginning, it says your IC, it is IB dependent. Your IC, it is IB dependent. Then I will go and say, now I need to go and find what is IB. Sorry. Yeah. Now I need to go and find what is IB. Yeah, sorry, IC, not IB, IC. For me to find IC, then I will go and say beta DC multiplied by IB. Beta DC multiplied by IB. Now, with these, then what is your beta DC? Your beta DC, with from the circuit, it says it's 120 multiplied by your IB that I've determined, which is 36,167 microamps, which gives me what?
4,340 milliampere.
4,340
milliampere.
milliamps. Any seconder?
Yes, sir. She's correct.
Good. Now, once you find your IC, remember this is IC, because I know you guys, when you are alone, then you said, but say there you wrote IB. This is your IC. Now, once you find your IC, then now you can go and say, with the continuation of these, now I can find what is my VC. And for you to find VC, then you're going to say VC will be given by your VCC minus your VRC, where VRC, it is IC multiplied by RC. Are we together? I hope we're together on that one. Now, then VCC, in this case, it is what? It is your 15 minus your IC, which is 4,340 milliamps, multiplied by your RC. In this case, we says RC, it is 2,7 kilo ohms, which gives you what?
Want to speak? I will speak. What did you say?
It's 3,282 volts.
3,282
volts.
Ma'am, are you sure?
Say.
Yeah. I want you to be sure.
Yes, sir. It's 3,282.
3,8.
3,282.
3,282.
Say.
Yes.
Before basa to dafa ange mrawobori mini not Steve mara bashimisa formula.
Aye.
Please, medium language of communication.
Yes.
Okay.
Answer. Yeah.
English yabo. Okay.
No. Medium language of communication. When I teach, I don't teach in mother tongue language. I teach in English.
Okay. Before you said it's not Steve.
Yes.
You use the formula of Steve.
Yeah.
Before we come here.
Yeah.
Last paper, you said not Steve, but
yes,
you use the formula of Steve.
Are you sure?
Yeah, I'm sure. Go back. Not Steve. You use the formula of not use the formula of Steve.
Where did I use the formula of Steve?
Step one, you said 144 kilo ohms is a not Steve, ne?
Mm-hmm.
And you say step 2, he said what? There's a 2 formulas, stiff and not stiff. And you use the stiff one.
Manier, can you reconnect with reality?
Hello?
Yes, I'm listening. Can you connect with reality? I've put everything that I've discussed with you here. Can you see what I put here?
Yeah.
Okay. Which formula of stiff and which formula is not stiff?
The one for stiff is VB equals to R2 over R2 plus R1.
Okay.
Multiplied by
And then
VCC. And not is VP, VB equals to R2 parallel to R in base. But as R in base is not stiff, you use the stiff one.
Are you looking at this?
Yeah, yeah.
So here, do you see it's R2 17,561?
Yeah, yeah.
No, I'm asking you. It's R2 17,61.
No.
So you said I use the formula of stiff, not stiff.
So I think he didn't see that thingy. Yeah, equation, the equation up there, the first one before that one.
Which one? This one?
The one, yeah. He didn't. I'm guessing he didn't see that one.
Manier, where did you get lost?
I got lost to like on the formula.
Which formula?
The one for stiff.
But this is the formula I wrote, right?
Oh,
What are you copying exactly where you are? No. It's not an embarrassment question. It's a normal question. What are you copying? Or what are you following?
like
People,
them
when I okay. Now I need your feedback. When I say something, do you understand what is coming out of my mouth?
Yeah.
But I specifically said, when I wrote here, I said what?
Not stiff.
Not stiff. Because it's not stiff, then we're going to do what?
R2 parallel to R in base.
Didn't I do R2 parallel to R in base here?
Oh, I got it.
Yeah. Are we together now? Yeah? All of you, are we together?
Yes.
Yes, sir.
Okay. Now, coming back to this one here. Now we're going to say, now we found what is VC. What do we find? That is VCE. Okay. Now you said VC is what? It's 3,28. You said VC is 3,282 volts, right?
Yes, sir.
Okay.
Yes.
Now, okay, good. Now, once we find this VC, then we're going to say, now we need to find what is VCE. Now, for you to find VCE, then it is going to be your VC minus your VE. For you to find VCE, it's going to be your VC minus your VE. Now, what is your VC? Your VC is what? 3,282 minus, what is your VE?
It's 4,510.
4,510
510.
volts. Then we should give you what?
Negative 1,228.
Negative 1,
One.
comma
228.
228 volts, which means that is your VE. Now, remember, as we have been discussing this, what is our aim? Now our aim was to push that this circuit of ours needs to work within what? Within the collector characteristic curve. Remember, your collector characteristic curve works on which quadrant? It works on the first quadrant. Are we clear? Are we clear?
Yes, sir.
Good. Now, then I will go and say, for me to determine this collector characteristic curve, for me to determine this collector characteristic curve, then I will go and say my collector characteristic curve will be based on the following categories or regions. I will have to find what we call the saturation region. I will have to find the cutoff region, and I will have to find the active region. Now, these are the three regions that define your collector characteristic curve. Up to so far, are we together? Now, for me to do that, then I will go and say, let me define the cutoff region. How do I define the cutoff region? I will define the cutoff region in this condition. Now, if that is during the cutoff, I will say if IB is equals to 0, if IB is equals to 0, now we know that IC, it is beta DC multiplied by IB. If IB is equals to 0, it simply means that your IC will also be what? Will also be 0. Are we together on that part?
Can you please repeat it, sir?
Which part?
The cutoff part.
Now, for you to determine the cutoff part, which is on your collector characteristic curve, then you will say when IB is equals to 0, when IB is equals to 0, because I see it is IB dependent, because I see it is IB dependent, therefore IC will also be 0. Do you understand that part?
Yes.
Now, if IC is 0, if IC is 0, what does it mean? Now, therefore, it simply means that when I am looking from the collector to the emitter configuration, where I'm looking from the collector to emitter configuration, my collector to emitter configuration will be given by the analysis that now my VCE will be the same as my VCC. Remember, this is the cutoff region. Are we together on that part? Now, in this case, my cutoff is what? What is my VCC? In your circuit, my VCC is what?
15 volts.
15 volts. This is during the cutoff region. Where is the cutoff region? Where is the cutoff region? Now, you will see that on your collector characteristic curve, and I hope you are following this. On your collector characteristic curve, remember, your cutoff region this is where your cutoff region is. That is your cutoff region, which means at this point here, when your IB is 0, then your IC will also be 0. Now, if your IC is 0, which means your VCE is equals to your VCC, which means it is going to be your VCE at cut off. And your VCC at cut off, which means it's going to be what? It's going to be 15 volts. Are we together on that part? Eh?
Sir, may you please
Yes.
repeat?
Which part? Which part are you not understanding?
Where we draw from, we draw in the collector curve.
On your collector curve, this is your IC and this is your, it's your current versus your voltage, or your voltage versus your current. That is your collector characteristic curve. Do you understand that part?
Yes, sir.
Your collector characteristic curve, it is the relationship between the voltage and the current, which means the collector to emitter voltage and your collector current. Remember, it is your collector current in relation with your collector to emitter voltage. That is your collector characteristic curve. Do you understand that part?
Yes, sir.
Now, for you to work on a collector characteristic curve, you need 3 regions. You need the saturation region, you need the cutoff region, and you need the active region. Do you understand that?
Yes, sir.
First, you need to determine the cutoff region. For you to determine the cutoff region, then you will go and say, when IB is equals to 0, which means you are assigning IB to what?
To 0.
Once you sign IB to 0, then you will say, now what will be my collector current? Your collector current, it is what?
It's 0.
It is base current dependent. That's why it says beta DC multiplied by IB. You still remember here, your IB is your IC, it is IB dependent. Do you still remember this?
Yes, sir.
Which means we are here. Then, because IB is 0, 0 multiplied by anything is what?
It's 0.
It's 0, which means here you have got 0 amps. Now, once you got 0 amps, then it goes and say, because IC is 0, therefore, your VCE will be given by what? Will be given by your VCC. Do we understand each other?
Yes, sir.
Which means your VCC, your VCE in this case is what? It's 15 volts. If your VCE is 15 volts, which means there I say 15 volts is that one there. Then we define when your VCE is equals to your VCC, that is your cutoff region.
All right. Thank you, sir.
Any question? Anyone else with any, again, another question before I move forward? Anyone with another question before I move forward? Okay. Now, once you do the cutoff, then the next step, you need to do the saturation. And for you to do the saturation, your saturation will exist. Your saturation will exist when the transistor has been switched on, which means when the transistor is a closed circuit. And when the transistor is a closed circuit, which means you will have your current moving from the collector all the way to the emitter, which means your current will be moving in that direction there. That is during the saturation region. Now, with this saturation region, then you will say, during the saturation region, I need to find what is my E saturation. So my IC saturation. Now, with your IC saturation, your IC saturation will be given by the following parameters. Your IC saturation will be given by the following parameter. It will be generated from the VCC minus your VCE saturation. Now, with the VCE saturation, it is the voltage which is measured before you switch on the transistor. Do we understand each other on that part? Remember, this is happening before you switch on the transistor, which means when the voltage it is gradually increasing, which means your transistor will remain at saturation. Am I making myself clear? Hello? Are you tired?
Yes, sir, we are fine.
Now, saturation will exist before the transistor gets, or before the diode start generating a 0.7 volt, because that is where the voltage will be. That is when now your transistor will be acting as an amplifier, which means before it gets to that 0.7 volt, which means your transistor will remain at saturation. Now, because that is happening, then you're going to say, what is the maximum current during that saturation? What is the V set? If your VC is set, it's not given. If your VC is set, it's not given, then we assume that VC is set, it's 0. If it's given, they will tell you what is the saturation voltage. But your saturation voltage, always, it will be below 0.7 volts. This voltage will move from 0 up to less than 0.7 volts. Am I making myself clear? Because once it reaches 0.7 volts, which means now your transistor starts to switch on, which means now you are having the active region. Am I making myself clear? Do you understand? Which means your transistor will remain, as long as it's below 0.7 volts, it will remain at saturation. The moment it jumps 0.7 volts, the moment it jumps 0.7 volts, which means now your saturation regions has fall out. Once your saturation region has fall out, which means now you are on the active region. Now, then we're going to say, during the saturation, then I will say VCC minus VCE at saturation. What is VCE at saturation? Now, you go and check. It's between 0 and less than 0.7 volts, which means anything 0.1, 0.2, 0.3, 0.4, 0.5, 0.6. But usually it will stop between from 0 up to 0.3. Now, once you get that saturation, then you will go and say, now divide by Now, I want you to look at this very carefully. Now, you will see that this is the current moving in this direction here. That is the current moving in that direction here. Now, if it is the current moving in that direction, which is your saturation current, you will see that it will combine your RC together with your RE. Now, here, then you will go and say, divide by your RC plus your RE. That is during saturation. Please don't confuse the formulas. Now, then you will go and say, what is VCC? VCC, it is 15 volts. Are we together on that part? VCC, it is 15 volts. Now, once VCC, it is 15 volts, then you will go and say 15 volts, then minus. What is saturation? Is saturation given? It is not given. Because saturation is not given, which means we'll assume that saturation is 0. If it was given, it was going to be told that your saturation, it is this value. Are we together?
Yes, sir.
Then from there, divide by RC. What is RC? RC in that case, it is 2,7 volts. That is your RC, 2,7 volts. Sorry, not 2,7 volts, 2,7 kilo ohms, not volts, kilo ohms. Plus, what is RE? In this case, it's 1,2 kilo ohms, which means now our IC set will be given by what? 12 minus 0 divided by 2,7 kilo ohms plus 1,2 kilo ohms. What will be the answer?
3,846 milliamps. 846 milliamps.
846 milliamps.
Milliamps.
Okay, which means now I'll go and say, let me move. Oh, let's say 3, it's there. 3,846 milliamps. That is this one. It is your I set. Do we understand the chart? Now, you have got I set and you have got cutoff. Now, the 2 points, when you join the 2 points, I want you to listen to me very carefully. When you join the 2 points, can you see? Your I set and your cutoff, your saturation and your cutoff. When you join the 2 points, now you need to determine, now you have set yourself to determine the active region. Now, this is that one there, that one there. Now here, you have created what we call a DC load line. Are we together? Are we together? Now, I want you to listen to me very carefully. Now, for the transistor to be active, then you go and ask yourself, where does it fall within the saturation and the and the cutoff region? Your VCE must not be equals to 15, and it must not be less than 0,7 volts, which means, let's say, for example, let me just write this here so that it can make. Now, the transistor will start operating at 0,7 volts. Do we understand each other on that part? Which means from here to there, that is saturation. Is that clear? This area here, that is your saturation area. Can you see what I've done?
Yes, sir.
Good.
Yes,
Now,
sir.
I want you to go back to our analysis, né? And I want you to tell me what is IC and what is VCE. Those are the two elements that is important to me right now. What is our IC?
I see, sir.
Yeah, IC, the one that you calculated. Remember,
It's 4,340 milliamperes.
4,340
milliamperes.
milliamps, isn't it? What is your VCE?
VCE.
Yeah.
It's negative 1,228.
Negative 1,228 what? Volts. Okay. Now, remember, when your transistor is operating, your transistor will remain at saturation. Your transistor will remain at saturation if the following it is occurring. Look at your IC. Your IC, this is your IC, which is the operational IC. Do we understand each other? This is your VC, which is the operational VC. Now, let's look. Remember, for the transistor to work, your VC must be between 0,7 and 15 volts. Must be between. It must not be equals to 0,7. It must be greater than greater or equals to 0,7, less than 15 volts. Let me see. For VCE to operate, I hope you will get this. For VCE to operate, it must be greater or equals to 0,7 volts and less than 15 volts. Do you understand that part?
Sir,
Yebo.
I wanted to understand the fact that you see that line section of the saturation.
Which one? This one?
Yes.
Yes. Yes.
In your calculations, you wrote a 0 instead of 0.7.
Where did I write 0?
Why? Towards the bottom of the page, when you're calculating VCE saturation.
Yeah, VCE saturation. Yeah. It's, remember, VCE saturation is from 0 to what? To less than 0,7.
Yes.
Were we given saturation voltage? Well, were we told what is the saturation voltage?
No.
We were not told. If we were not told, we assume that the saturation voltage, it is what?
It's 0.
It's 0. If we were told, then we were going to replace this 0 with the value of the saturation voltage, but it must be in between 0 and 0,7 volts. Do you understand that part?
Yes. So if they give us a number, how would that graph change?
Which graph?
Let's say they give us 0.2. What happens to the graph, the saturation region?
The saturation region will stay there. Nothing is happening on the saturation region. Maybe I'm failing to understand your question. When you say what will happen to the saturation region?
I'm saying, so if they give, if at this point in time they don't give us VCE saturation, so we assume it's 0.
Yes.
Let's say they give us VCE saturation and they say 0.2. How does that affect the graph that we draw?
It doesn't affect the collector characteristic curve.
Oh, okay. That's fine.
Did I answer you? Did I answer you?
Yes, sir. Yes,
okay.
Sir.
This is just to indicate that this region, this is where you will find your saturation point.
Yes, sir.
Okay, good. Now, people, did you understood this one here? I don't want to confuse you. Did you understood this one here? VCE will operate when it's greater than 0.7 volts but less than 15 volts. Did you understood that part?
Yes, sir.
Okay, good. Now, let's look at VCE. Where is VCE? Our VCE is what? Minus 1,228 volts. Can you see where it is? Which means, remember, minus is where? If this is 0, where is minus? Minus is going to be somewhere here, isn't it?
So we can't see the paper.
Which part of the paper can't you see?
Like the paper that you're writing on, we can't see.
You can see.
Yeah.
It's blurry.
Only.
Yes, it looks fine from my side.
Anyone else? Are you seeing blurry?
It's
It's blurry,
okay.
sir.
Eh?
It's okay.
It's also blurry.
Oh,
Is it blurry? Is it okay? Is it not okay? Is it blurry?
I
Which
think
one?
it's their
It's
network.
okay
It's
now.
okay.
Now it's fine.
Masiwa, it's fine. You can continue.
I think it's your device. Ma'am, can you sort out your device?
I think the camera focus.
Or they can no longer focus. Ne? 2 hours is too
I
much. I
don't
know.
know. The camera focus. That camera
okay.
is focusing and focusing.
Or their camera. No, my camera is fine. Okay. Now, I haven't shifted anything. My camera is fine. Remember, if it's minus 1,23, you will see that it has even shifted on the negative side. Now, if it shifted on the negative side, which means it has run away from the operational point. Which one is the operational point? It is within the DC load line. Remember, you want your transistor to stay between the saturation point, which means between this point. Let me find another thing. Okay, there. Now, you want your transistor to work between these points here. That is where you want your transistor to work. Here, that is where your transistor must work. Can you see? Because this is where the active region is. Are we together on that part? Hello?
Yes, sir.
Now, already your VCE has moved out, which means if your VCE has moved out, and also you will see that your VC has even exceeded your IC saturation. Can you see? Now your IC is 4,340, which means it's even above, because your I set is 3,846 milliamps. This one is somewhere here. Your IC is somewhere here, which is 4,348. So 4,340, which means your transistor, it is staying within the saturation region, which means now I can go and say if IC is greater than I saturation, then your transistor, it is at what we call saturation mode. Are we together? Hello?
Yes, sir.
Yes, sir.
Are we still together?
Yes, sir.
Now, in this case, it simply
Yes.
means that your transistor never went out of saturation. Your transistor stayed at the region of saturation, which means in this region, we don't know at which point it is your transistor generating an output, because it stays within the saturation. Now, within the saturation, it simply means that now your collector to emitter, now it says going forward, it says during the saturation region, you will see that your collector to base configuration, it is at forward bias. I want you to listen to me very careful. Your collector to base, it is at forward bias, and also your collector to emitter, it is forward bias. Then you have forced the transistor to stay into saturation. Am I making myself clear?
Yes, sir.
Now, this whole equation, what we have done, now we have calculated that this transistor of ours cannot give us a specific result because it is within the region of saturation. Remember, for the transistor to go into this active mode, for the transistor to go into this active mode, which means your collector to emitter configuration, so your collector to base configuration must be reverse bias, then your emitter to collector must be, your base to emitter must be at forward bias, so that you can have the results of the collector to emitter there. But now, based on this calculation of ours, then we have seen that, which means this magnitude that we have here, it is forcing our transistor to go into saturation mode. Now, when it is at saturation mode, which means I can go and manipulate one or two values so that now I can take this transistor of mine out of saturation into active region. Now, for this transistor to go into active region, remember this is saturation region, to go into active region, then the active region will say when your IC it's less than your I saturation, then that is when you have got operational mode, which is your active mode. Operational mode or active mode. That is when your IC set it's less than your I saturation, which means when the current of IC is between 0 or greater than 0 but less than I saturation, which means if I find IC from here to there, If I find IC from here to there, that is when you find your IC. This is where you find your VCE. Now, this region here, we call it an active region. As long as your current will lie within these points here. Can you see these points here? As long as your current will lie within these points here, which means that is your active region.
Sir,
Yebo.
Is it possible that you find IC that lies within the point of 0 and Z I saturation, but the VCE lies out? Let's say for example my IC is equal to 2 milliamps.
Okay.
And then
yes.
and then my VCE is still that negative 1,228.
Yes, it can happen.
So how does it affect the curve, the graph?
There will be no graph. Remember, your graph, it must be the relationship between the VCE and the IC. Now, for your voltage, let's say you find that VC is here, IC is there, which means, okay, let me put it this way. Where your IC meets your VCE, that is the point of operation. Now, let me just say this. If I go and say this is where my IC is, which means when your IC goes like this, it needs to meet at that point there, which means that point there. That is your Q point. Do you understand what I'm saying right now? IC and VCE must have a correlating relationship within the DC load line. What if they don't touch both of them, they don't touch the DC load line? Both of them, not single. If both of them, they don't touch the DC load line, which means your transistor, it is at saturation. Or your transistor, it is at cutoff. Am I making myself clear?
Yes, sir.
Any question up to so far?
Sir, what if my IB is not equal to 0?
Eh?
What if IB is not equal to 0?
If IB is not equal to 0, which means IC is not also equal to 0.
Okay.
Isn't it?
Yeah.
So which means now you have moved from what? You have moved from cutoff. Anir?
Mm-hmm.
You are starting to have drop in what? You are starting to have drop in VCE. When you drop VCE, you increase your IC. I remember the last time when I was speaking to you in class, I said, when you increase in IC, you drop in VCE. You still remember?
Yes.
Yes, that is what is happening. Remember, the moment this IB starts to generate, which means your VCE also will change. Because you have got IC, then you will see that for you to find VCE is going to be this one minus that one there. When you drop this VCE, When VCE is dropping, your IC it's increasing. When your IC is increasing, which means also your IB it is increasing. Are you following me? Eh? Are you following me? Okay. Let me take another example. Anli? Anli?
Yes, I'm here.
Can we push to 10?
Yeah, you can to
Okay,
10 o'clock.
No, 10 o'clock. Can we push to 10 o'clock?
Yeah.
Let me just give them 2 minutes break. Yeah, sorry, 5 minutes break, and then we can come back and continue. But I don't think we must stop. Yeah, you can have 5 minutes water break, and then we'll come back and continue. You can we pause it, the video, or we just leave it recording?
Okay, I'll pause it.
Yeah, let's just have 5 minutes break. According to my watch, it is 9 o'clock, which means by 9:05, then we continue again.
Yo,
Yeah.
hey.
What is wrong? Okay.